Is that an eagle? We are doing a LiDAR scan followed by a 3D oblique digital twin model of some fairly rural, I mean, this is about as rural as it gets. Did you go ahead and, while I'm talking, pan around there? This is a two parcels, the pair of which is a little over 4 acres. And this is one of the benefits about being that drone guy. So I'm doing a study for me about these parcels right here. They're down the road a little ways, right there, but as you can see, the topography, I should say, is kind of like this. It's very steep, and it looks like it levels off about halfway up, but the LiDAR scan will tell us that in gory detail. And then what I'm doing is providing a bare earth model and a digital terrain model, digital surface model to the GC that's going to tell me what it's going to cost in order to grade this, cut and fill, leveling, all that stuff, and remove the, if we do, remove the indigenous trees and so forth. But the nice thing about it is I'm using the Matrice 400 today, and this is kind of the state of the art right now, the Zenmuse L3 LiDAR scanner. Here's what that looks like. So this is I have 3 400s now, and this one is specific to the L3 because, there's the L3. It's a frame-based LiDAR sensor, dual 100 megapixel cameras, angled so they give almost 180 degree view. 100 megapixel. I mean, it is the schnizzle, as they say. Okay, so let's strap this on here. The reason that I have a purposed drone is because this gimbal right here is specific. Gimbal holders are specific to the L3. Nothing else really runs really well on it. So I just figured, let's have a drone that's dedicated to it. We do enough LiDAR stuff to justify it, so. Okay. Oh, this LiDAR is for collision avoidance. That LiDAR is for gathering data. Put a fresh battery in there. Load it into the launch position. And, oh, look at that. We got up to more than 25 satellites. That's nice. That was yellow a few minutes ago. Now it's green. All right, I'm coming right behind you there, hon. Launch pad. I got these 2x2 foot 3/4 inch plywood pieces at Lowe's when I was up getting our PPE stuff upgraded, and I'm going to put black and white tiles on here and turn them into ground control points. In addition to it's a perfect platform. You can see this thing fits on it perfectly. Of course, when it has that pattern on it, the pattern recognition inside the drone will also use it to land, which is good. It's going through its little gimbal test. I was on RTK data. I could have used RTK data in the entire mission, but I need to record the positional correction data, the RTK correction, so that I can do some ground truth later on. We're going to do an opus correction of this occupation today. I think we're probably going to be here about an hour and a half or hour and 15 minutes. So we're going to do we're going to be here probably for at least an hour and 15 minutes. And that's enough to get a good set of correction data out of here, an OBS file that I can send off to Opus, National Geodetic Survey, Opus, to get corrections, so I can make sure that, because this is a point cloud and I'm handing it to a general contractor, so we have to have some proof that it's viable, and that's why I'm changing from RTK data to this. And I'll use RTK data to configure this to within a couple of centimeters of where it actually is. The correction shouldn't be that big, but what's important is the proof, is the data set that shows where you were and prove that you were working correctly. All right. We got a manual calibration, but we're going to do a custom network RTK with RTK data calibration. And what that does is uses the N-trip service in RTK data to locate that base station to within a couple centimeters, and then from the base station to the rover is sub-centimeter. It's a couple millimeters. So once the corrections come in, I'm going to have, last I looked, I think I got like a 4.5 millimeter accuracy in horizontal, and I can't remember, 5 centimeters vertically, which is pretty good. But it'll be really nice. It's a way that you don't really have to worry about ground control points when you do this, because it's pretty good. Okay, so we're all connected up now through that. That has been configured. Now what I have to do is go out and pull up the flight route. I think I got this all set up, but let's just check it. LiDAR mapping, ortho, 150 feet, terrain follow. AGL, terrain follow. Course angle looks good. Advanced settings, let's do 80-80. Okay. Bypass obstacles, 150 foot, and we're doing 350K sample rate, linear mode with photo resolution of 6K and 16 returns. Man, this thing is a beast. We should be able to count the pebbles with that resolution. Okay, ready to go. That's got to be 600 points per square meter. I have to figure that out, but it's pretty robust. Okay, now I have a wire right over top of me, so pay attention to what I'm doing here. Clear? Oh, wait a minute. Yeah, I'm RTK'd. There we go. Yep. All right, so let's see how high we are here. $150 feet. This sucker's gonna, I'm glad I called the sheriff's office, because that's all the higher it's gonna be right there. Yeah. So, here we go. It sure is. That's right. looking good. It's doing its calibration. See the jogging back and forth? Can you see it from down here? Well, it's jogging. I'm going to do the point cloud and the I'm going to let the point cloud go back and forth. Oh, that looks really good. It's so resolved. Yep. This is really going to be a good data set. Stay out of my way, Mr. Hawk. You look pretty cool, but don't make me beat you. All right, it's starting. Yeah, the point cloud looks really good. Okay. We can sit for a few minutes. Yeah, let's sit in the car where it's nice and I can see and all that. Make sure I keep an eye on this sucker. He's a little low for my taste. Well, everybody pretty much knows. I mean, if they're knowledgeable at all about building, then they know that in order to build, you obviously have to clear. You can't build in a field with a bunch of trees in it. And then in addition to that, you also have to have a flat surface to build on. Or you have to accommodate the fact that you don't have a flat surface. Some people build on a hill, but they build the house where the basement's out, you know, but the basement's underground here and it goes down. So all that topography, all of the terrain, you need to understand it. And what this does is it is flying right now and taking LiDAR. And you can see this. The left is the LiDAR scan. What it's doing right now is it's sending out 350,000 points per second and receiving returns up to 16 returns. LiDAR is a laser-based detection and ranging system. In fact, that's what it stands for. It's L, capital L, little I, capital D, capital A, capital R. So light, detection, and ranging. And what it has in it is a laser. And the laser sends out pulses. And the pulses are fast. This one is 350,000 times a second. And then for every single pulse, you can get up to 16 returns detected. So if the pulse hits it comes down, hits a leaf, continues on, hits a branch, continues on, hits another leaf, continues on, all the way down to the ground. Every one of those returns you get back. And so what those returns are, when you have a laser pulse go out and you get a return back, it creates a point in space with 3 dimensions assigned to it. X, Y, so that's a horizontal, and Z, how high. So it's a point in 3-dimensional space. The collection of those points is called a point cloud. And every point is geospatially tagged. So you know exactly where it is, not only on the Earth, but above the Earth. And you get this picture, basically, of what the land looks like. Now, since it's laser and since it's its own light source, you don't worry about things like shadows and clouds and, I don't know about fog, but you don't worry about the same things you would worry about in a picture. In a picture, you're taking pictures, you're a photographer. And then there's algorithms that take those pictures, and based on where the picture was taken and what the picture shows, it tries to infer where all the points are. This doesn't do that. This sends out laser ranging things that tells you exactly where the points are. So it's very, very specific. And what it allows you to do is tell how steep something is, whether or not there's something in the way. If it is in the way, the exact dimensions. And when I say exact, I'm talking with this RTK base station back here, we're getting sub-centimeter accuracy. And I'll find out later. Well, actually, I could probably tell you. Let me see. We're going to here. The standard deviation right now for X and Y is 0.007. So that's it's 0.006 on the X and 0.08 on the Y feet. So that is 6/1000ths of a foot. A thousandth of a foot is 0.012 inches. And 0.012 inches is about a half a centimeter. So 50 millimeters. Or sorry, 5 millimeters. By the way, a millimeter, if you take a dime is about a millimeter thick. So it's 5 dimes stacked up. That's the accuracy we're getting in X and Y directions. It's like this. And that's because I'm using an RTK base station. And then what I was explaining earlier, the RTK base station is configured in its place back here with an N-trip service. That is it's a service they're called caster service, casting services, caster casting. And what they do is they have continuously operating reference stations all over the place. And it generates a pretty good location center for where your stick is, the stick being the survey stick back there. And the survey pole in the middle of that tripod is calibrated. So I know to like 1/2 of a millimeter or something that thing is exactly 2 meters high, and that's where we get the reference for the vertical. The point is that this is survey quality stuff. And the point cloud shows you exactly what this terrain looks like. Now, once you have that, there are several collateral outputs from that point cloud. One of them is a digital terrain model, or DTM. Another is a bare earth model, which basically is what's the ground look like underneath all the foliage. There are other collaterals associated with that, contour maps and TINs, and that's a triangulation of points on the ground to show you where the slopes are. You can use those for hydrology studies. You can show where water is going to flow. You can feed all that information into a CAD system, a computer-aided design manufacturing system, and it will tell you exactly what you have to do in order to level that ground. And so that's actually what we're doing up here today. That's the main output of today's activities, is I'm going to give this to a general contractor friend of mine who is going to take a look at these collaterals, and I'm going to put it into, we have a software package called Virtual Surveyor, which basically does this stuff for you, almost. You have to play with it a little bit, but it's pretty accurate, it's pretty simple. And then I can tell him things like, you need to move, X number of tons of material from this position to this position, cut and fill, it's called. If you have a slope like this, where this is the high point, this is the low point, basically to make a flat surface, you've got to take material from here and put it here, cut, fill, and then you get a flat surface on the thing. So this would cut and this would fill, and you'd have I can't do it, well, maybe, yeah, well, I'm trying to do it with my hands. That's kind of funny. See, you can do that. So this part's still here, but the part that was going down here has now been moved, and the part here has been filled, and so it's flat. And that's what you need in order to build a house. And then, of course, the other thing is you got hydrology studies which allow you to say the water's going to flow this way. Well, you don't want the water flowing into your basement, so you divert it around. So we're almost finished here. Looks like we got about 12 seconds. I better get out and land the drone. It's doing its final, it's calibrating the IMU one last time before it lands. I don't know why it does that, honestly. Maybe it's tying up the point cloud, making sure that it has data at the end of the collection. I would imagine that's what it's doing. And we're just going to bring it over here and land it back on its little pad. Now, I never let it land by itself. I always take control. Today will be no exception. I got this wire right here, and I don't want to mess around with that. So I'm going to bring it past me, come out in that clearing. Honey, will you keep an eye that way for traffic? I hear something coming. Is there something coming? I hear something. Okay. I'll watch this direction, you watch that direction. Okay. Well, I'm out of the road now, so it's okay. This is a little tight on here. I think I'm going to land on the ground. Just landed here. Need to land it on that guy. Hey, man. Yeah. We're doing a LiDAR survey scan of this 2 parcels here. Yep. I have to put my wood away. This is going to make a nice ground control point. I bought 4 of them, but I'm going to get like 8 more. We'll drill a little divot right in the center for the survey stick. Then we can do an occupation, opus correct it, and we'll have the thing to the exact coordinates the surveyor would. From then on, you can use photogrammetry to correct your point clouds and other things.